Okay, another conservation momentum problem. This time it is in 2 dimensions. So this is a nice one to begin with because only one of the objects is moving at first. So we see here we have a 0.7 kilogram block initially at rest on a frictionless surface. It's struck by a 0.4 kilogram puck that is initially moving in the positive x direction with a velocity of 3 meters per second. After the collision, the puck has a velocity of 1 meter per second directed 32 degrees above the x-axis, the positive x-axis that is. What's the speed of the block after the collision? We're actually going to find the velocity, the speed, and the direction in this case. Well, drawing a good before and after picture is always helpful in conservation of momentum situations, explosions, or collisions. And these were already drawn for us. So as we see, we have the ball moving, we have the block sitting still, and actually it's a puck, I guess, a puck. And then the puck moves up here, where this angle is 32 degrees. That's 32 degrees. And this velocity is 1 meter per second. It's a little bit off the screen, but you can see it. And we want to find out how fast is this block going. So what's the magnitude of its velocity? And then we'll also find out that angle right there. Well, this is a collision. We have masses and velocities. That makes it a good candidate for a conservation of momentum problem. Now, when you conserve momentum, all the momentums initially, actually it should be lowercase p for momentums. All the momentums initially will equal the sum of all the momentums finally. Now, these are vectors. So to do normal algebra, we have to break it into components. We can't just add up all the vectors. We have to add up the x components and then the y components. So we're going to first do the x's here. If we add up all the momentums, not the forces, all the momentums initially in that x direction, that will equal the sum of all the momentums finally in that x direction also. The order of the subscripts isn't essential. So here we have puck and block. So I'm going to say we'll have the momentum in the x direction of the puck initially, lots of subscripts, plus the momentum in the x direction of the block initially will equal the momentum in the x direction of the puck after the collision plus the momentum in the x direction of the block finally, or after the collision. So before and after, that's going to match our before and after pictures. Before here, all the momentum is in the x direction. Now momentum is mass times velocity, so this would be the mass of the puck, the velocity of the puck in the x direction initially. We'll get to the numbers in a second here, but let's make sure we do all this symbolically, make sure we have things right. And that would be added to the mass of the block, the velocity of the block in the x direction initially, which is 0 because that velocity is 0. And that's going to equal the momentum of the puck times the velocity of the puck in the x finally, mass of the puck, velocity of the puck, not momentum, plus the mass of the block, the velocity of the block in the x direction finally, which is what we're looking for to get to the end. That's the first step. Now we can put in all the numbers we know. So this is 0.7 kilogram block, and it's moving in the x direction at 3 meters per second. And the block is not moving, its momentum is 0. Afterwards, puck has that same mass, 0.7. Its velocity is 1 meter per second, but we just want the x. The x is going to be this horizontal component over here, which is the adjacent side, so that's going to be using cosine. So we're going to say 1 cosine 32 degrees. That is the velocity in the x direction of the puck. Now, the block, we don't know. But we can write in here, we got some, we don't know the angle, we don't know anything, so we know that its mass is 0.4. Whoop, we've got a mistake, right? Got a mistake. The block is 0.7, the puck is 0.4. This is the puck moving. So good thing I caught that. Some of you probably caught it earlier. That's 0.4, this is 0.4. So keeping, this is a lot like accounting it, to keep all your numbers straight. Now here the block is the 0.7. That's 0.7, and it has a V of the block, X. That's what we've got to find. That's final, but it's the only one, so I'm going to drop that final subscript. And now we just plug in some numbers and figure that out. 0.4 times 3 is 1.2. That 1.2, we got 0.4 times 1 times the cosine of 32. That's going to give us 0.3392. I'm going to take it out extra digits, and to that we add the 0.7 VBX, and when we work that all out, we get 1.297 positive. Does that make sense? Yeah, that's the X. The X should be to the right. Positive makes sense. Positive 1.2297. I'm always going to carry out some extra digits, and actually in my calculator I'm going to go back up and select the whole number. I won't round off till the end to the significant digits. Now I have to do that same thing for the Y direction. So I'm going to just adjust the camera here so I got a little more space for the work. Same process for the Y's. So all the momentum in the Y direction initially, Y, will equal the sum of the momentums in the Y direction finally. So in the Y's, we've got the puck Y initial plus the block Y initial, and we'll have the puck Y final and the momentum of the block Y final. These are both 0 because there's no Y motion here, and this isn't moving at all, so we're going to have a 0 plus a 0. And then in this case, we're going to have the mass of the puck, the velocity of the puck in the Y direction final, and the mass of the block, the velocity of the block in the Y direction final. So this left side is all zeros. The puck, remember, is 0.4. The puck is 0.4 kilogram mass, and its velocity in the Y direction, that would be this component of its velocity, and that's opposite that 32 degrees. So that's going to be, I'm running out of lead. Should repair it. Going to switch here. That's going to be 1, the speed, times sine of the angle, 32 degrees. Make sure you're in degree mode. And to that we will add the mass of the block, that is the 0.7, and timed it by its velocity in the Y direction. And when we work all that out, we get that the block in the Y direction is a negative 0.3028. And negative, that makes sense. If the ball, the puck, went up, there was no up, no Y velocity, no Y momentums at the beginning. There has to be a net, or a sum of the Y's at the end have to be 0. So if this had a positive, this has to have a negative. And that matches. Now that's its velocity, so we can find the speed by doing the Pythagorean theorem. The overall speed of that block is found by the x's squared, y's squared added together, taking the square root of that. So take the one, square it, add it to the other. And again, I'm actually going back and pulling out all the digits. So I get that this speed is 1.2664, but it looks like we have two significant digits. So, whoop, sorry, over here, that's 1.2664, which is 1.3 meters per second with two significant digits. Now, if we want to find that angle, oh, get some glare from the lights, can't read those numbers. That's a little better. To find the angle it's making right here, that theta is going to be the inverse tangent of the opposite velocity over the adjacent velocity. So that's the inverse tangent of the y, which is this, it's this one, the y. Now I'm going to put absolute values in and use my brain to figure out the angle. So I'm going to use this magnitude, this y, 0.3028, 0.3028 divided by this x, 1.2297. And when I plug those in and take the inverse tangent, second inverse tangent of the 0.3 divided by the 1.229, 13.8 degrees, 13.8 degrees, which is 14 degrees with two significant digits. So there we have it. Conservation of momentum in two dimensions. Just like one dimensional, you got to do it both. You got to do the x's and you got to do the y's. Got to break up things into components or use the components you know or are given. Combine them back together using Pythagorean theorem and find that angle using inverse tangent. Hope that was helpful. We'll see you next time.